In this video, we are going to explore combined energy calculations in a problem that involves heating a sample. So this problem states that we need to calculate the kilojoules needed to melt 25 grams of ice at 0 degrees Celsius, warm the liquid to 100 degrees Celsius, and then convert it to steam also at 100. So right here, the 25 grams of ice, that is a unit of mass. So it is giving us the variable m, and everything else we'll need to piece together from the rest of the problem. The very first thing that we want to do is take a look at the heating curve that is listed below and identify which areas represent which state of matter. So for example, if we're looking at the 0 degrees Celsius range, that is the melting point of water. So in this region right here, we have melting. And that means that anything below 0 is going to be solid. That's when water is going to be ice. If we go above 0, it will be liquid. And if we look at the 100 degrees Celsius range, that is the boiling point of water. So that means that this region right here is boiling. And if we go above that, water will be in the gaseous state and will be converted into steam. So then we need to identify what is happening in each region of the heating curve. So if we are looking at the melting process, when we are melting something, we have a mixture of a solid and a liquid. And during that process, we have a phase change. We're going from a solid into a liquid. And you may notice that during a phase change, there is no change in temperature, because as you are melting the solid, the liquid is warming it up, but the solid ice is also cooling the liquid down. So until that is completely melted, there is no temperature change. That would be just a change of 0. So during that process, we are going to use the equation Q equals mass times the heat of fusion. And the heat of fusion is a value that you would look up in a reference sheet that might look something like this. So you may notice that that equation is listed right here, and then the value for the heat of fusion is given right here. And which value you use depends on which unit you need for your problem. So we do have the value in calories per gram or joules per gram. Now in this problem, it's asking for kilojoules. So once I get to the point where I'm plugging things in, I'm going to use the joules per gram value. If we are in the boiling process, then we have a mixture of liquid and gas. So similarly, this is a phase change, and because there is a phase change, there's no change in temperature. So we're going to use a very similar equation. Here it's going to be Q equals mass times the heat of vaporization. And the heat of vaporization is a constant that is representing the boiling process. So for that, we would use this equation. And there are two values for the heat of vaporization, just like with the heat of fusion, and which unit you select depends on which unit the problem is asking for. So since here the problem is asking for kilojoules, we're going to use the value represented in joules. For everything else, there is no phase change. There is only a temperature change. So for example, if we are in the region of less than 0 degrees Celsius going up to 0, all we're doing is taking a very, very cold solid and warming it up to a less cold solid. But it's still a solid. There's no phase change here. So here the equation that we're going to use is Q equals mc delta T. So that is going to multiply our mass, the specific heat of the solid, and the change in temperature. And that equation is listed right here on our reference sheet. Now we'll have to be a bit careful when we're using that equation to determine whether we're using the specific heat of water or the specific heat of ice. And that will depend on which phase we're in at that particular moment. So we'll come back to that. Same sort of thing will be happening in the liquid state. So if we're going from 0 degrees Celsius up to 100, we're going to be in the liquid phase. We're just warming up that liquid. So the equation that we'll use is, again, mc delta T. And same in the gaseous state. So as long as there is no phase change, we're using the Q equals mc delta T equation. So let's dissect what's going on here. And I like to draw myself little pictures to identify what is happening, where are we currently, and where are we going. This is telling us that we have ice at 0 degrees Celsius. So I'm going to sketch that. It'll be a terrible drawing of ice, but that's okay. Here are some weird looking ice cubes. Okay, so we have ice, and the temperature right now is 0. And the next thing it tells us is we need to warm the liquid to 100. But in order to do that, if we are right here, so we have ice in a solid state, we're at 0 degrees Celsius, this is the point where we currently are. If we're going to get all the way up to 100, the first thing we have to do is to melt that ice. So that has to turn into water in order to get that water to 100. So the first thing we're doing is melting. And I'm just going to draw that right here. So here we have the melting process. I'm going to call that Q1. That's the first thing we're doing. And during the melting process, this is the equation that we are using. So for Q1, we will have mass times the heat of fusion. And then I'll doodle myself another picture where that water has been melted into ice. So now we have water. And notice that during the melting process, there is no change in temperature. So that water is still at 0 degrees Celsius. It has not changed the temperature. Now we want to get that ice to, or the water, to 100 degrees Celsius in order to convert it to steam. So now we're in this region of the heating curve. And notice here we do not have a phase change. It stays in its liquid form. It just gets hotter. So the equation that we're going to use is Q equals mc delta T. So I will draw that right here. So here we are heating. And the equation for that part is mc delta T. And that will take us into hot water. So now that water will be at 100 degrees Celsius. And the last thing we need to do is convert that water into steam at 100 degrees Celsius. Now at 100, we have the boiling point of water. So that is the region of the heating curve that we are dealing with here. We're going to boil it to convert it into steam. And then we stop there because it's saying that this is happening at 100, which is right here. So we're not going past that. We're not heating it any further. We're just going to convert it into steam. And the equation associated for that is the mass times the heat of vaporization. So my Q3 here will be mass times the heat of vaporization, and that is for boiling. And at that point, we will have steam. That was not a good rectangle. And again, because there is a phase change there is no change in temperature. So this is all going to occur at 100 degrees Celsius. Okay, now that we have that and we've dissected everything, we have all the equations, now we're going to look up these values and plug them in. And notice that the problem is asking for kilojoules. So all of the reference values that I look up are going to be in the joule format so that I can avoid any excessive unit conversions. Okay, I'm going to do this step by step. So for melting, we said our Q. So I'm going to look that up. And it looks like we're using the 334 joules per gram. And the mass just came from the problem. That was 25. So 25 grams times 334 joules per gram. You can extend that line out so that it can be very easy to see which unit is where. And notice that grams are up top and on the bottom, so grams are going to cancel out. So we're going to multiply 25 by 334. Okay, when we plug that in, I'm getting 8350 joules. Now you have a couple of options here. You could convert that to kilojoules immediately, or you could convert at the very end. Doesn't particularly matter. For the next step of the process, we have the heating. Ooh, not the highlighter tool. And the equation for that was Q is equal to mass, times specific heat times the change in temperature. Now notice that here we're going from 0 to 100 degrees Celsius. So the change in temperature is just 100 because all you're doing is subtracting out 0. The mass was 25. That doesn't change. But now we need to look up the specific heat value. And this is where things can get a little bit easy, a little bit tricky because it's easy to miss which specific heat value you need. Notice that at that point, we had already melted that ice, and that is now water, which means that the specific heat value we want to use is the one for water, not the one for ice. And because it's asking for kilojoules, I'm going to use the value that is expressed in joules. So that was 4.184 joules per gram per degree Celsius. And you want to include that entire unit. And I recommend doing it in this format where you have a horizontal line clearly separating them so you can see which unit is in the numerator and which one is in the denominator. And finally, I'm putting in the change in temperature, which was 100 degrees Celsius. I'm going to extend this line just to make it a little bit easier to see which unit is where, and then we'll cancel stuff out. Notice grams are on the top and on the bottom, so they cancel out. And then we have degrees Celsius on the top and on the bottom, they cancel out. And that's exactly what we want because we want the units to be in joules. Okay, I'm getting 10,460 joules. And I'll just copy that over to the next page so we have everything in the same spot, and then we'll do this for the boiling process. Okay, for boiling, our equation was Q equals mass times the heat of vaporization. So I'll copy that over. And mass, as usual, was 25 grams. And then we'll look up the heat of vaporization. And that value in joules is 2260 joules per gram. So I'll plug that in. Okay, and now we have grams in the numerator and denominator, so they will cancel out, and our heat is expressed in joules. And when I plug that in, I get 56,500 joules. Now to get the total heat, all we're going to do is take these values and add them together, and then we can convert them to kilojoules at the very end. Will be the sum of Q1, Q2, and Q3. So we will add them all together. And that gets me 75,310 joules. But notice that the problem was asking for kilojoules, so we need to convert that. And we know that the prefix kilo means 10 to the 3, which is 1,000. So that means that 1 kilojoule will be equal to 1,000 joules. So all we really need to do is divide that by 1,000. So since joules here are in the numerator, I need to put them in the denominator to get them to cancel out. And once they cancel, we are dividing the 75,310 by 1,000. And that will get us 75.3 kilojoules. And that is the end of that problem.